have a return visit from Alessandro Tricoli, who received his undergraduate degree in physics from the University of Bologna in Italy, of course, and his Ph.D. in particle physics from Oxford University. He worked as a research associate at Rutherford Appleton Laboratory in the UK and as a research fellow and then staff member at the European Organization for Nuclear Research, which is known as CERN, in Switzerland, receiving commendations on his excellent performance from both institutions. He joined Brookhaven National Laboratory on Long Island in 2018. In 2017, Alessandro was awarded the Early Career Award from the Department of Energy's Office of High Energy Physics for a project with the ATLAS experiment at the Large Hadron Collider at CERN Laboratory. His work aims to improve the search for exciting new physics beyond what is currently described by the standard model of particle physics. He plays an important role in the upgrade of the ATLAS detector using novel state-of-the-art silicon technologies capable of precision particle tracking and timing so that the detector will be better able to tease out new physics signals from the background events. Designing these next-generation detector components could also have a profound effect on the development of future instruments in several scientific applications. Dr. Tricoli is also a co-author of multiple publications and has extensive experience coordinating large groups of physicists involved in research in the ATLAS Corporation. He is passionate about tutoring and mentoring young physicists and is active in science outreach. Thus, his presence here with us today, for which we are very grateful. Alessandro, please know how grateful we are, and we welcome you, and we'll turn it over to you at this point. Thank you.
Thank you very much, Penny, for the nice introduction. Can you hear me well?
Yes.
Good. Okay, so I get started, and so thank you again for having me here. I want to talk today about dark matter and the fate of the universe, and you will see that the fate of the universe really depends on how much dark matter we have in the universe. But before doing that, I want to show you that the different conception of dark matter in the public opinion. And something funny occurred to me last Thanksgiving. So I received an email in my inbox, and the title was dark matter, ... So I opened the email and I read what you see here. Remember, we have dark matter. So I was very curious, and there was a link, which you should never follow a link in an email from somebody you don't know who sent me this email, but nevertheless, I was curious. So I did that, and I clicked on that link, and let me show you what that, for a second, stop sharing, and I share something else. What the email showed was this. So that link from to the website, remember we have dark matter. Very nice animation, and then very, very dark, minus 25%. Booking with promo code, the Blackest Friday. So yeah, this is not the kind of dark matter we'll talk about today. What I will talk about today is dark matter in the universe. But it's funny that really appeals to the public. So let me go back to my presentation. Okay, so now let's start with visible matter. Matter that emits light, for example, matter from stars in the sky. So if you look very early in the morning at the sky, you'll see something like this, the Orion constellation, very big constellation. You see Orion on one side and chasing the Taurus, the bull in the sky. And one of the elements of the Taurus is the Pleiades, a group of 7 stars called the 7 sisters, daughters of the Atlas, a Titan Atlas that holds the world on his shoulder. And these Pleiades are a cluster of stars, that are far away, about 400 light years away from us. What that means? It means that light takes 400 years to come from those stars all the way to us. So when we look at the star and then look at the sky, we look in the past. So the light that was emitted from the Pleiades that we see now was emitted 400 years ago. So pretty much at the time of Elizabeth I in England, or Galileo Galilei in Italy, and William Shakespeare in England. And but if you look at other stars, for example, Betelgeuse here in the Orion constellation, this is a giant, a red giant, very big. In fact, it's so big that if we could put Betelgeuse where our sun is, it would engulf the orbit of Mercury, Venus, Mars, and Earth, and probably even Jupiter. So it's a giant, red giant. And it's far away, about 700 light years from us, a bit more. So it means that the light that was emitted from Betelgeuse started from that star at a time when Italy was Renaissance and China the Ming dynasty. So we're going further and further away. And in about 100,000 years, Betelgeuse will explode in a supernova, emit gas and particles and materials in the sky, and it will become a bright object, much brighter than it is now, after it becomes a supernova. We have to wait, though, 100,000 years to see that, but it will be very interesting. And what will happen, it will become something we can already see here, down here, still in the Orion constellation. There's an object here, which is a nebula. This is what Orion, the Betelgeuse star, will become after exploding into a supernova. So let's look at this Orion Nebula. As I said, this comes from an explosion of an old star. And what's very interesting in the universe, that material is recycled. So this is in fact a star incubator. So if you look down inside, zoom in the core of this nebula, we see some young stars are born. These are very young stars, about 1 million year old, which is very little for lifespan of stars. So many stars are born here in this nebula. And by the way, the light of this nebula that we see now was emitted about 1,500 years ago. So it means the light that we see now from this nebula and from those stars that are being born from that nebula was emitted when in Europe there was just about the fall of the Roman Empire. So again, when we look in the star, we look in the past. Something also very interesting in this nebula is the protoplanetary system. So we see here, if we zoom in around one of these stars, we see a protoplanetary system. The same as what our planetary system was about 4.5 billion years ago. So we have different filters of the same image. And you see here on the right-hand side, there's in the middle, a bit more light coming from the star, and around is an edge-on view of materials that spin around the star. And eventually, in few billion years, this will become a planetary system. The same way as we have in our solar system. This is a pictorial representation of our solar system about 4.5 billion years ago. And then with time, this gas, materials, objects form planets as we know of now. And this is our current planetary system. But also we know that our sun is a tiny little object, the sun, among a huge amount of other stars, in fact, 250 million stars, sorry, 250 trillion stars in a galaxy, which we call the Milky Way. And again, all this I'm describing now is what we call ordinary matter, matter that emits light. We haven't discussed yet what is dark matter, but first we have to understand what matter is in order to understand what dark matter might be. And also, something which is very dark in the universe, we call black holes because they're black, still ordinary matter. But what are black holes? Black holes are objects that are so dense in mass that nothing can escape from it, not even light. So everything spins around these massive objects. You see here at the top, this black hole with gas and material spinning around, and they feed the black hole that becomes larger and larger. And we believe there's a supermassive black hole at the center of every galaxy, including our galaxy. So black holes are very important for galaxy formation because we believe they are so massive that had a huge contribution in galaxy formation, attracting the stars in galaxy formation. But what are black holes in more detail? So if we could exemplify our space and time and represent it as a foil, and we put the sun on this foil, the foil will deform. So the space and time is deformed. If we add objects traveling like our planet Earth, orbiting around the sun, will feel this deformation and means will orbit around the sun. But if the speed is sufficient, will not fall in the sun. But if we have a black hole, the curvature of this deformation of space and time is infinite. I mean, it's like a hole in this foil. So nothing can escape, not even light, if it gets too close to the black hole. That's why I call black hole, because nothing can escape from it, and it's black. But again, this is still ordinary matter. We can tell, for example, if we could compress the mass of our sun to be just 4 miles in diameter, our sun will become a black hole. So it's still ordinary matter. But how far can we look into the past? Can we look all the way to the beginning of time? So this is one of the best pictures. They look at the deep sky. And what's very peculiar in this picture, there's 2 different layers. If you see this white object, these are galaxies. These are in the foreground. These are galaxies in a cluster of galaxies, which is about 1 million or 2 away from us. But behind that layer, there's another layer of galaxy. Those are more blue color, elongated or strange shapes. Those are 12 billion light years away from us. So the light from those galaxies was emitted when the universe was very young, about 1 billion years old. So really an infancy of the universe. And we are able to see so far away with the Hubble Space Telescope because of very peculiar property of gravity. So these stars in the foreground, these white stars, thanks to their mass, they act like lenses called gravitational lensing. They deform the light coming from far away stars and they magnify their light so we can see far away stars, galaxies, which are very, very far away, 12 billion light years away from us. So let me explain this a bit more because this will become very important to understand understanding of dark matter. So if we have this our Earth, this Hubble Space Telescope, we look at a galaxy. This is a foreground galaxy about, in this representation, 3 billion light years away from us. And then further away, here 11 billion light years away from us, we have another galaxy just behind it. The light beams from the distant galaxy are represented with this red line, are deformed by the gravity of the foreground galaxy. And they are deformed, so they bend. So our view corresponds to these pink lines. So what we see, in fact, not the distant galaxy, but we see many blobs which represent the same galaxy, come from the same distant galaxy, but it's like going through a lens that a bit distorts the image. It's not really well focused. So the single picture of a galaxy is distorted in several different images. In this case, there are 4 different blobs of light. Another presentation I will see later, will see can be full rings. So this view is deformed, but also is magnified. So this foreground galaxy acts as a big lens. And this will be very important for understanding of dark matter. So remember gravitational lensing. This will come back later on in this presentation. And so this allows, the gravitational lensing allows to see very far away, 12 billion light years in the past, but still very far away from the beginning of time, which we call the Big Bang. And the question is, can we see all the way to the Big Bang or very close to it? So let's break down in a timeline the history of our universe. So we believe our universe was born by quantum fluctuation from effectively nothing. And a massive explosion that created a soup of fundamental particles that were entangled together. Even light was entangled in this primordial soup, it could not escape. But at some point, about 400,000 years after the Big Bang, atoms were formed. And at that point, light could escape in straight line and come all the way to us. So this picture that you see here, colorful in blue, green, and red colors, this is all this time you can ever reach by observation. Beyond that, the universe is opaque to our eyes. And then afterwards, with a bit more later on in time, stars started to form thanks to nuclear reactions, and then galaxy, cluster of galaxies, and then the universe expanded all the way to us. And later on, I will go in more detail about this expansion of the universe. It's still a mystery. So this is, again, a picture of this layer here, the ultimate time that we can ever see with observation of the sky. This is called a cosmic microwave background. It's a picture of the universe when it was 400,000 years old. And it's like looking at a picture of ourselves young. It's difficult to recognize the universe here, as it's difficult for us to recognize ourselves when we were young in an old picture. Nevertheless, we can still see some characteristics that are still there in our current universe, the same way as we can recognize some traits or characteristics of our face in a picture of ourselves when we were young. For example, these different colors, red and blue, show different temperatures in the universe, which were there at the beginning of time, so when the universe was very young. And these different temperatures then became differences in the density of the universe. And that led to the formation of clusters of galaxies and galaxies themselves. So understanding of this picture at the beginning of the universe is very important to understand the universe the way it is here. And in order to understand this picture, we understand dark matter. Because if you look at the sky now, at the very macroscopic level, we see this type of picture with superclusters of galaxies and big voids in between. It's called a big web, the cosmic web. And again, this structure that we see nowadays, this is a drawing from a simulation, but a pretty good representation of the current universe nowadays. And you see some analogies between this picture and the picture I showed you earlier. And again, dark matter plays a critical role for understanding of this large-scale structure of the universe now. But to understand this and go beyond that limit of 400,000 years after the Big Bang, we have to go and look inside us, look at atom level in the world where gravity plays no much role, but quantum physics plays a bigger role. Through these experiments that we can do in a lab, we can do Brookhaven lab or CERN laboratory in Geneva and in other places, we can reproduce the conditions of the universe much earlier in time, way beyond the 400,000 years that we can achieve by observation. We can go to fractions of a second after the Big Bang. And so to do that, we have to understand the atoms and the nucleus of the atom. So here is a representation of the atom. We have electrons orbiting around the nucleus of protons and neutrons. And these objects are very small. If we compare the atom, size of the atom with the size of a penny, it's similar to the size of a penny with respect to the size of the moon. So that very tiny object. That's why different laws of physics apply at the scale of atom with respect to the scale of humans or scale of galaxies or clusters of galaxies. For those people who attended my previous lecture, I'll revise a little bit what I explained before because it's essential to understand dark matter. So if we look at inside the nucleus of the atom, we have protons. And protons are not fundamental particles. They're made of other particles, 3 in our case, called quarks. And these quarks are different types, and they are held together inside the proton by a very strong force we call gluon. So I said, people who attended my lectures, hopefully it will be just a revision of what I discussed, but this is very important to carry on and discuss about dark matter. And the Brookhaven lab, we can reproduce the conditions of a soup of particles that existed a fraction of a second at the beginning of time. And in fact, now the Department of Energy has awarded Brookhaven lab with a new accelerator that will become operational in 15 years or so, will be one of the biggest microscopes that will allow us to look inside the nucleus of the atom and we understand the strong force that holds these fundamental particles together inside the nucleus of an atom. And this is a multi-billion project will bring jobs to Long Island, in addition to doing great research in fundamental physics. And here what you see is the building blocks of the universe. This circle represents all the fundamental particles of the universe. And if you need to build your house and you need to you need to buy building blocks, this is all you need. You need these type of particles like quarks, different types, up, charm, top, down, strange, bottom, funny names. They're very similar in properties, but these are fundamental particles. And then we have the electron, of course, and its siblings, the muon and taus, which are identical to the electron, just a bit more massive. And then other particles, neutrinos, which are very lightweight and feebly interact with matter. But what you have to take from this picture is just these are the fundamental building blocks of the universe. But then we need to have forces to hold them together. And at very fundamental level, these forces act as interactions. So if you have 2 people on 2 boats and exchange a ball, you will see these 2 people slowly moving apart. You can say they're exchanging a force. And at fundamental level, in quantum physics, these 2 people could be 2 quarks inside the protons. They exchange a gluon. So there's a force that holds them together or pulls them apart. This is how fundamental interactions work in quantum physics. And this is a summary of all our interactions, the way we know of. So we just met the strong interaction, the strongest interaction in the universe. It holds particles together inside the nucleus of the atom. And the carrier of this force, the ball that is exchanged between the quarks, is the gluon. Then we met electromagnetism. We are familiar with electricity, magnetism. If you stick a magnet against your fridge, it doesn't fall. This is due to the force we call electromagnetism. And the carrier of this force is a photon. This is the quantum of light. And then there's a weak interaction, which is responsible for radioactive decays. And then there's another force, which we're very familiar with, gravity. But it's also very mysterious because we haven't found the particle that is responsible for this interaction. We call it graviton, but we haven't discovered it yet. And this is a holy grail in particle physics. So going back to the circle, we have building blocks of the universe. We have fundamental forces, and the whole, now, since the whole house is in place, we can building blocks. We have the glue that holds the building blocks together. We can build the house. But there was a fundamental problem in 1964. Until that point, this picture seemed to be broken because all these particles, according to our theory, we call the standard model of particle theory, they're all massless. But in laboratory, we could measure the masses of all particles. We knew these particles are massive. So again, there's something missing in this picture. And at that point, in 1964, people said, well, just throw the standard model away. We have to build a new theory. Nothing is good. But that there were three clever theorists which said, no, let's keep the standard model. It's still valid. And in fact, it's one of the most accurate theory that can be tested in the lab. But we need to add another particle we call the Higgs boson. Let me discuss what the Higgs boson does. So let's take this picture. We have a room full of physicists spread in the room. And at some point here in the middle, we have a scientist coming in. And then at some point, there's a news that the Nobel Prize was announced, and that gentleman is a recipient of the Nobel Prize for his discoveries. So as you see here on the right-hand side, all the other physicists cluster around that famous physicist to shake his hands and congratulate. And clustering around, they slow down that poor man who wants to walk from one side of the room to the other side of the room. So this is happening in the so-called Higgs field. So Higgs field is representation of all these physicists around the room, is everywhere in space, fills the whole universe. But when the particle travels in space, the Higgs field clusters around that particle and slows the particle down, giving mass to that particle. So the Higgs boson, which is a fluctuation of this Higgs field, gives mass to particles in the universe. So now we have a beautiful theory that can describe the universe and fundamental building blocks of the universe. And this was found many years afterwards. The conceptual representation of the Higgs boson was discovered in 2012 at Stern Laboratory just outside Geneva. This is a huge accelerator that accelerates protons and makes them collide at the highest possible energy, so high that we can reproduce the conditions of the universe very close to the beginning of time. We call it a Large Hadron Collider. Underground is about 16 to 17 miles in circumference. And this is an animation that shows two proton beams colliding, generating many particles, including the Higgs boson, that leaks to a very tiny little fraction of a second, show it again, and then decays into flashes of light, two photons. These two yellow lines represent the two photons. They are emitted from the decay of the Higgs boson that leaves a tiny little fraction of the second. This is how the Higgs boson was discovered. And this allowed these two gentlemen to be awarded a Nobel Prize in 2013. This Professor Higgs from Edinburgh, this Professor Engelert from Imperial College, two of the three that discovered the Higgs boson in 1964. Unfortunately, the third one died prematurely. And this is one of the experiments that discovered the Higgs boson, called the CMS. So now we have a beautiful picture of the universe. Coming from the standard model, we can reproduce the condition of the universe close to the beginning of time, a tiny little fraction before the beginning of time. But still, the standard model, despite being one of the most successful theories ever invented and ever tested by human beings, still has many unanswered questions. And one of these questions is dark matter. What we know is that so far is only ordinary matter, which makes only 5% of the energy of the universe. 5 times more energy is in the universe is coming from dark matter. So what is dark matter? In a word, we do not know what it is, but we know many properties of dark matter, but still has to be found. So let me explain here why we believe there is dark matter in the universe. Let's look at a galaxy, like our galaxy, for example. The speed of the stars in a galaxy depends on how much material, how many stars there are in the galaxy. So at the beginning, so if you go to the core of a galaxy, there's not much speed of this galaxy. But the further away you go from the center of a galaxy, here in the light years, the more speed or velocity these stars have. They go all the way up to 200 kilometers per second. This is this red curve. But then just base our judgment on the matter that we see that emits light, so stars, we would predict the velocity or the speed of these rotation of stars in a galaxy would go down far away from the galaxy. At some point it will go to 0. So there's no more matter when you're very far away from a galaxy, around 1,000 light years. So there's nothing to orbit around. But then it's not what we see in experimental data. What we measure is this white line. So what we measure is that stars far away from the core of a galaxy still have very large, high speed. So they rotate much faster than we would predict. So it means there must be more mass in the halo of the galaxy. Matter that we do not see as light, but still is there and makes the stars rotate much faster in the halo of the galaxy, the periphery of the galaxy. That's why we call it dark matter. But also, if you remember the gravitational lenses that we saw earlier on, this fundamental principle of gravity, now it's very useful to understand dark matter because look at this picture. Take, for example, this one, the top left. We have in the middle a galaxy, very bright. And then we have this ring around. This ring is coming from a galaxy right behind the galaxy, is much farther away, for billions of light years away from us. And the light is distorted and magnified at the same time and makes this very beautiful circle. But if we just look at the light that comes from the star, from the galaxy in the middle, we would think that there's not enough matter to make such a beautiful ring. So we need some extra matter around this galaxy here in the middle to produce this beautiful ring around, coming from the galaxy further away. So in order to see these beautiful effects in the universe, like what you see here, the matter, ordinary matter that we can see through light is not sufficient to generate such beautiful pictures. We need more matter. And this we call dark matter because it's matter that we do not see. And this is another beautiful picture. This is called the bullet cluster. So here, in fact, is 3 pictures superimposed. What happens here, we have ordinary light that we see all these beautiful galaxies. Then we have in pink a picture from X-rays. And then we have in blue a picture from gravitational lensing. So what we see here is these 2 clusters of galaxies colliding and getting past each other. So what happens, these are clusters of galaxies, thousands of galaxies in 2 clusters that collide and get past each other because there's a lot of empty space between them. But in fact, this apparent empty space is full of gas, hydrogen, materials. And when these 2 clusters of galaxies get past, this material in between galaxies in the cluster gets heated up and produce X-ray. And this is what we see with this red or pink picture. But then we can look at the gravitational lensing effect. So how much mass there should be there given the gravitational lensing effect that we see from far away galaxies. And this is what represented in blue. And what you see, the blue and the pink are not superimposed. They're in different regions of space. So it means ordinary matter that produces a ring, this pink color coming from heat, so ordinary matter, is very different from the matter that produces this blue object. This is effectively coming from dark matter that creates gravitational lensing. So this is a beautiful picture that really, again, proves there is more than ordinary matter in the universe. So far I gave you 3 examples why we believe there is a dark matter. However, we have not discovered what dark matter is, but we know also it must be very important in shaping the large scale structure of the universe. If you remember at the beginning, I showed this simulation, this cosmic web. This is in fact real data of the cosmic web. So if you take every of these points in this picture is a galaxy. And in 3 dimensions, you see they are shaped as a Swiss cheese with regions that are depleted from galaxies, and other regions where galaxies, a cluster of galaxies, are more dense. And we believe this shape was there at the beginning of time. Remember this picture of a cosmic microwave background that is at a time where this structure was taking shape and then governed the rest of the evolution of the universe. And dark matter played a critical role here because dark matter is 5 times more abundant than ordinary light, ordinary matter. But again, we do not know what dark matter is. We know its properties by observing the universe. But for understanding what it is, we need to go back to particle physics, go inside the nucleus of the atom. This is where the answer of what dark matter is will come from. And maybe another theory. So if you remember our circle with our ordinary particles, this the circle with the building blocks, and the quarks and electrons, muon, taus, neutrinos, and then inside we have the forces, the photon, the gluon, and the weak force, and the middle Higgs boson. Well, most likely this picture will break down, and maybe we'll have other particles around that will explain why dark matter exists and what dark matter is. So to understand dark matter, we have to again reproduce dark matter in a laboratory like CERN laboratory, just now outskirts of Geneva, Switzerland, or Brookhaven Lab, or at Energy Frontier. There's something even more mysterious. I mentioned earlier, that we only know 4% of the universe. About 27% comes from dark matter, of energy in the universe, but almost 70% of the energy in the universe comes from something that we do not know what it is. And this is dark energy. And other than its name, we know very little about dark energy. But why do we know that there is something called dark energy in the universe? Well, we know because of the expansion of the universe. Dark energy is a force or an energy that counteracts gravity and makes the universe expand at a faster pace than expanded at the beginning of time. So now this is a picture, as I showed earlier, of the energy of the universe. Dark energy is about 70% of the whole energy in the universe. It means it's making the universe accelerating at a faster pace. And maybe this dark energy will increase more and more, so will drive the fate of the universe. But what is interesting is that if we go back in time, again here, when the cosmic microwave background was generated, so only 400,000 years after the Big Bang, there was no dark energy. The universe was dominated by dark matter, as represented here. So here 63% of the energy of the universe was coming from dark matter. So if you remember what I said earlier, the large scale of the universe that we see now was shaped already at the beginning of time, when the universe was only 400,000 years old. And at that time, dark matter was the dominant matter of the universe. And that's why we believe dark matter has shaped the evolution of the universe and shaped the large scale structure of the universe all the way to us. But from this point onward in time, dark energy will have bigger role and may drive the fate of the universe, even more than dark matter. So in this representation is that you see some galaxies, and in green you see the space-time deformation coming from dark matter and the matter that emits light, ordinary matter. But also there is something else, this pink grid, which is a dark energy. This is everywhere in space and time, and is a force that pulls space and time apart, makes the universe expand, pulls galaxies away from each other to counteract gravity. So then I'm transitioning towards the fate of the universe to understand what is the future of our universe. So let's draw the line of time, the present time, and then here's the past. So this star is the Big Bang, the beginning of time, and the universe expanded, we know, driven by dark matter. The question is what will happen in the future. So it could well be, if there was no dark energy and the matter, especially dark matter, was sufficient in the universe will recollapse in a big crunch. But we know this is not the picture of our universe. We know there's dark energy that makes the universe expand. So this is maybe a more realistic picture of our universe. The universe expands, and a critical universe means just enough energy to make a not collapse into a big crunch. But again, this picture is not fully in agreement with the data because we know there's dark energy that makes the energy of the universe much larger as time goes by, makes the universe expand. So this is maybe a more realistic picture where we have a coasting universe, the stars and galaxies are pulled apart and the universe expands more and more. However, if dark energy would expand at faster pace, then we have accelerating universe, where it expands at an exponential regime. And in fact, if dark energy expands at very fast pace, they could be pulling apart very fast galaxies and stars. But we believe we're not in that regime. Dark energy so far is accelerating as fast as this to rip apart the whole universe. So we believe we are in a picture which is in between coasting universe and accelerating universe. So with this picture, you understand that dark matter has driven the evolution of the universe and the large-scale formation of the universe, but also at some point in time, for some mysterious force that we still do not understand, dark energy came to be, and that will drive the future and the fate of the universe. And with this, I conclude. I want to show you in just a few minutes a film that will go through what I described so far, go through the timeline of the universe from the very beginning of time, the Big Bang, all the way to the present time. And then from that moment onwards, we'll go in more speculation based on our theories and our observations and lab measurements. And we'll go into the future and we'll try to extrapolate our understanding to the very end of time. So let me start this film. At the bottom, you will see shortly timeline on the left-hand side, on the right-hand side, some text that explains what's happening, but I will talk over. So this is the Big Bang. It's coming from the fluctuation of the vacuum. A massive explosion where created our universe. And then gravity became the strongest force and started attracting particles. At some point, the universe expanded at an extremely high pace, very rapidly, and cooled down at the same time. Now here, the fundamental forces, the electromagnetic force, weak force, strong force, became independent forces. And here you have a soup of fundamental particles. The quarks here are getting together and forming protons, neutrons, forming the nucleus of the atom. You see this primordial soup of particles, and also light could not escape, was bouncing around in this primordial soup. But at some point, atoms were formed, and electrons started orbiting around nuclei, forming atoms. At that point, light would escape, and this is cosmic microwave background. So we could see finally light coming from the universe. And that a bit later, first stars were formed when the universe was only 2 billion years old. And then very mysterious and massive objects like quasars, which we believe have in their core supermassive black holes, were formed. In the beginning, galaxies were very small, much smaller than our Milky Way, for example. At some point later on in time, the Milky Way was formed, so our galaxy. And we believe at the center of our galaxy, we have a supermassive black hole, pretty powerful engine of our galaxy. And this Andromeda galaxy, very close to us, and in 5 billion years, the galaxy will collide with our own galaxy. And then there was a massive explosion of a whole star in a supernova that started the formation of our planetary system. And it's our sun that has material spinning around, and then after 4 billion years or so, the planetary system as we know of came to being, and this is the Earth. And at some point in time, in a collision between our Earth and another planet, debris were scattered around, orbiting around the Earth, and then from these debris, the moon was formed. And then we are getting to our present time. And now we go into the future, until the end of time. So Betelgeuse, the star we met at the beginning, in 100,000 years, will explode in a supernova. Our sun will also increase its luminosity, will become brighter and brighter. So brighter and hot that life will not be more possible on Earth, but may be possible in other planets or other satellites further away from the sun. And so the Andromeda galaxy eventually will collide with the Milky Way. And at some point, our sun will become a red giant, will engulf the Earth. What we see now. And then our sun will end its life becoming a white dwarf. But before then, as you see from these pictures, maybe life will be possible in outer planets in the solar system. At some point, the sun will become a white dwarf. And then due to expansion of the universe, the stars will move apart more and more. Galaxies will move apart more and more. And at some point, there will be no more star formation. All the stars that we know of will die, will explode in supernovas, will become white dwarfs or black holes. And little by little, the galaxies will lose material due to the dark energy. And then the supermassive black holes at the center of each galaxy will little by little eat up the material that is around it, become larger and larger, but those black holes will die, will evaporate in so-called the Hawking radiation into explosion of particles, slow explosion of particles. There's some point when even black holes will evaporate and all galaxies will be so far apart due to the stronger and stronger dark energy, the universe will be black, dark, and not much else to see other than black. But at some point, maybe in the future, there will be another quantum fluctuation of the vacuum, and maybe, who knows, maybe a new Big Bang will occur, and maybe a new universe. And with this, I conclude today's presentation. Thank you.
Well, thank you very much, Alex. And I'm assuming, I believe there are some questions. We have a couple of comments in the chat box. One says, oh, hello, Penny and Yvette. Good to see you. Gravitational lensing proves that gravity is a push rather than a pull. Can you talk to that view? Do you see that question?
Yeah, I see. Well, it's both ways. You can see now, even now, right? You can see that when you have a satellite, and we want to send satellite from Earth to outer planets, what you do, for example, from Earth to Jupiter, what you use a gravitational pull or push to get speed. So your satellite gets close to Mars orbit and gets a push from Mars, so accelerates and can go all the way to Jupiter. So you can use gravity that way as well. But what happens in gravitational lensing is that it's a deformation of space and time. So light, rather than traveling at linear direction, will bend like the orbit of our planet will bend in orbit around the sun. But this bending of the light happens only if you have a huge amount of mass. It's a distortion of space and time that causes this effect.
Alex, could I ask a question?
Absolutely.
Here's my question. Because you've studied this subject and are involved in exploring the universe, do you give thought to some original creative force in the universe? Is that part of your thinking and wondering?
Well, yeah, so what we based our judgment is on observation and on data, on experiments. So what I can tell you is that we are investigating the origin of all forces. And what is very interesting, we have found that there's a common principle, fundamental principle that gives birth to all forces in the universe. So that means the force I described earlier, the weak electromagnetic force, the strong force, and gravity comes from the same origin, same principle. Now, since we have a common principle that gives birth to all forces, we can think about unification of forces. So at higher energies, these forces can become one. We only see that as different forces now at lower energies in our world, but maybe at the beginning of time, we're a single force. And we have evidence nowadays. So we really managed to unify electricity and magnetism in a single force called electromagnetism. We also already unified the electromagnetic force with the weak force. We know they're two different faces of the same coin. Maybe in the future we'll be able to unify other forces. So our hope is at some point, maybe in the exploration at the Large Hadron Collider, we'll be able to unify all forces, have a theory, grand unification theory, or also a theory of everything that could explain why these forces came to being. And maybe it's just we see it as different faces of the same coin, but ultimately they are the same force.
Okay. I want to give people chances to ask questions. So I see Roger has a question. What about light having a mass, since it is a partial, which means this equation is in question, E equals mc squared?
Well, so light, as we know,
I'm sorry, it was particle, not partial. Yeah. Okay.
Yeah. So the light, photons, the way we see light, those photons have no mass. Nevertheless, they are subject to the deformation of space and time. This is why the straight line of the light can be deformed, and we have this effect of gravitational lensing. So photons that we know of have no mass. However, there's something peculiar, and maybe is what Roger is referring to. We have so-called virtual photons. These are photons that live a tiny little fraction of a second. They're not photons that we can observe through light. Are photons that are created for a tiny little fraction of a second and then disappear immediately. Those photons are massive, can have mass. But those I would call virtual photons, photons that are not real, are not detectable by our eyes, but can live for a tiny little fraction, but we can see their consequences in experiments at the Large Hadron Collider. So yes, some peculiar type of photons, we call it virtual photons, can have mass.
All right, do we have some more questions?
People can also maybe
You can
raise their hand if they have questions.
unmute yourself, I believe, if you have a question. And just speak up because I can't see.
If you have questions and you don't want to write in the chat, just unmute yourself and ask a question. Or raise the hand or wave.
Well, let's see here. I don't see any questions right now. Oh, no, I don't see a question here. All right, Alex, I mentioned a book earlier on, and some of the guests today may be interested in this book by Donovan Moore, and or in his program about this woman who was an astronomer. And if you go to our website and click on adult programs, and then you can click on view our collection of adult program recordings, you can look through the list until you see Donovan Moore. So anybody who has a problem with that, let me know. But I'd love if we were able to answer some more questions, but I just don't see if there are any people who have a question.
We'll have tours in August. Yeah,
if you have a question, maybe, you have maybe put your question in the chat.
There's a question of whether Biennale will have tours in August. Yeah, every summer we have open days. It's unclear to me whether we'll have yet. So we'll have, if there are, will be advertised on the website. So if you search for Brookhaven National Lab open days, you will see if they are advertised. Usually it's in August. But this year, due to COVID, things are different. So we haven't reopened fully, so only essential people have returned to BNL. So I believe this will not happen this year. But if it happens, it may happen at the end of August. That's my guess. But I invite you to check on the website. Things change on a day-to-day basis, yeah.
Well, I would say for those of you who have suggestions about more topics related to tonight's topic, be in touch with us at the library, and we'd love to invite Dr. Tricoli back here. But in the meantime, this was a very fascinating talk, made as simple as you could make it for an audience such as us, I would say. You did a very good job making that clear. So I want to thank you, Alessandro, and also thank you all for being here tonight. And we will hope to see you again, and wish everybody well and stay safe, and we will keep in touch.
Thank you very much for having me. And if you have questions, don't hesitate to send me an email. You can easily find on the web, or Penny can forward that to me.
I can help anyone who's trying to reach Dr. Tricoli. So we'll say goodbye to everyone. Thank you again so much.
Thank you very much.
Okay. Bye-bye.
Bye-bye.